This is a facility called the Canadian Light Source. The CLS is one of the biggest scientific projects in Canadian history. And what its $174 million facility is designed to do is to shoot electrons around what looks like an enormous racetrack. And as they speed along inside that track, they give off intense beams of light that scientists can use to learn more about electronic and molecular structure. In other words, this facility literally and figuratively shines light on chemistry. Alright, so it may come as a bit of a surprise to you, but the vast majority of what we know about molecules and how electrons are structured around all the nuclei that we've been learning about, the vast majority of information that we know about molecules comes from light. It comes from the interaction of light with matter. So, as you know, some matter glows, but also some matter absorbs light. So matter can emit light and matter can absorb light. And it's that process of emission and absorption that is critical for us to understand, how electrons are structured around molecules, and even how molecules are structured themselves. So things that we know about chemical bonds and how strong or weak they are, and if molecules have reacted or not, and things about the energies of electrons. All of this comes from light. So what we really need to do today is start by reminding ourselves all about light, everything that we know or think we know about light. So first, let's remember what light is. It was Einstein that taught us that light is actually comprised of tiny little units called photons. Okay, so photons are the smallest indivisible part of a beam of light. So a beam of light is made up of billions of these tiny entities called photons, right? So you can almost think of it as a particle of light or a tiny chunk of light. And he was able to deduce this, this is actually what he won the Nobel Prize for. It was for his investigations into something called the photoelectric effect, which really simply is just as you shine light on metal, you can eject electrons off of that metal. So this is sort of the basis of what solar panels are built on. But the whole point of that was that light must be comprised of these tiny indivisible units. And so these photons, or these particles of light, is really what light's all about. And that's important for us because it's those photons, it's those individual pieces of light that will do the kinds of interactions that we need to learn about. Okay, so these photons, they travel through space. And we know from our work in high school and other courses that light behaves like a wave. And I think there's some misconceptions among students about what that really means. So if I've got a photon, and suppose this is my photon, as it travels through space, photons travel through space in a straight line. Okay, so light shines in a straight line. And a lot of students sort of imagine the light might be traveling through space as a wave. A lot of students sort of imagine the light going up and down like this. But that's not true. The wave properties of light are what it's called its electromagnetic field. Okay, and so that can be a complex topic, but really electromagnetic field is just almost like an electrical charge that this photon is exerting over time. So we just imagine that as this photon travels in a straight line through space, what's happening is its electric field is oscillating, right? So at one particular point in time, it has a positive, it's exerting a positive electromagnetic field. And then as it travels a little bit farther, it's exerting a negative electromagnetic field, and then positive, and then negative, and then positive. So this oscillates back and forth. This is really, what we mean when we talk about the wave nature of a photon, or the wave nature of light as it proceeds through space. And so the interesting thing here is that if a photon, if we want to think of this as a particle of light traveling through space, exerting a positive electric field, and then a negative electric field, and then a positive electric field, it's probably not surprising that this photon should interact with molecules. Atoms and molecules have positive and negative charges built right into them. So as the photon, becomes in the same space as molecules, they'll interact because of these interacting electromagnetic fields. So let's think about what are the relevant properties of the wave nature of this photon that we should really keep track of here. And so if we look at this oscillating electromagnetic field, one of the things we notice is that there is a point on this wave that matches an adjacent point on the wave. Okay, so the peak, for example, will repeat over and over again. Now, I've not drawn this wave perfectly to scale, but the point I'm trying to make here is that there is a distance, a literal distance, a physical distance between identical points on a repeating wave. And this is known as the wavelength, which is given the symbol lambda. It's a Greek letter lambda. And so this wavelength is, as I said before, a literal distance of how much distance does a photon have to travel before its electric field starts repeating itself. Okay, so that's called the wavelength of a particular photon. And of course, if I were to draw a different example here, let me change my color. If I were to draw a different example down here of this photon traveling through space, maybe it's a red photon, you could easily imagine having a much longer wavelength, okay, much longer wavelength of a photon like that, okay, and so this wavelength is actually, not even on the page. Actually, let me redraw this in a way that's going to make a little bit more sense. Let's try this way. There we go. So still not perfectly to scale, but in this particular case, we've got a much longer wavelength for this particular photon, okay? And so this wavelength is a characteristic feature of the photon. I can say that I've got a photon of a particular wavelength, and that tells me a lot about its properties. First and foremost, we can actually relate energy to wavelength. So if I think about how I can relate energy to these wavelengths, well, it's the black one here is oscillating much more quickly, right? And it's the red one that's oscillating more slowly. So I think it's intuitive to think of the red one as actually having less energy. So the red one is a less energetic photon. It's sort of lazy in how it oscillates its electromagnetic field through space. And so I think we can intuitively imagine that the bigger the wavelength you have, the smaller the energy you have. So if I needed an equation to relate this, I would probably say, well, the energy of a photon, and by the way, these equations are well known, you would have seen them before, but the energy of a photon as it relates to the wavelength should be inversely related, right? So as the wavelength gets really big, the denominator in this fraction will get really big, and the energy of a photon will consequently go down. And that's true. And what the numerator looks like, the numerator on this relationship here is really just a constant. But it's for our purposes, it's actually two constants being multiplied together, h and c. So h is Planck's constant, and c is the speed of light. So the values of these constants, just to keep a note of this here, the value of Planck's constant, or h, is 6.626 times 10 to the minus 34 joules seconds. So that's joules multiplied by seconds. Kind of an odd unit system, but it's the kind of unit system that you really need to do the conversion back and forth between lambda, which is a distance, right? There's a length unit to lambda, and energy, which obviously is an energy. So there's an energy unit to the E, and that's joules, which is in this Planck's constant. So that's going to be useful for us. Now the other constant is c, speed of light. Which we can all, I think, remember as 2.99 times 10 to the 8th meters per second. And again, I don't ask you to commit constants to memory, but nonetheless, there they are. And so this is a relationship over here that allows me to convert between wavelength and energy. So again, probably you've seen this before, but nonetheless, it's important for us to know about this. So now, we can literally equate the wavelength of a photon to its energy. And as you're probably aware, the wavelength of a photon is also equated to its color, per se. Okay, so the different colors that we see, the different colors of light that we see, are really just different photons of different wavelengths hitting our eyes. Okay, so some, red photons have a certain wavelength, and green photons have a certain wavelength, and so they're very, very characteristic. If you tell me the wavelength of a particular color, we know its energy, and that wavelength, that color is inextricably linked. So then there's one other property, I suppose, of these waves that really we should talk about, and it's very much linked to this notion of wavelength. And that other property that I wanted to talk about is something called a frequency. So frequency is given the symbol nu. This is a Greek symbol. It's kind of like a V blowing in the wind. Okay, so that's what this symbol looks like. And what frequency is as the name implies, so let me just indicate that here. So nu is the frequency. Frequency is literally that. How frequently does this photon oscillate its electromagnetic field? Okay, so how frequently does that field oscillate? And so I think we can just sort of intuitively imagine that if the wavelength is really long, like the red one, then as the photon travels through space, its frequency or its oscillations are not as frequent. Right? Whereas with the black drawing that I've indicated up above, as it goes through space, the electromagnetic field oscillates very, very quickly, so that we would say that would have a high frequency. And that's exactly right. And because we know that the speed of light is fixed, so all photons travel at the same speed, the red one, the black one, they're all traveling at the same speed, that allows us to relate the wavelength to the frequency directly. So we know that these have to be related. And so the wavelength and the frequency can be related fairly simply by using the speed of light. So if I take the speed of light and divide it by the wavelength, that is really what the frequency is. And this should make sense. If I zoom in on this relationship here, our frequency is often in a unit system of hertz. And hertz is given the symbol Hz. So if I were to just indicate the units here, we could call this frequency in units of hertz. And what hertz actually are is 1/seconds. So really think of it as per second. So if I'm expressing a frequency in hertz, what I'm asking is how many times per second does this electromagnetic field oscillate on this photon? Okay, so that's what that means. Now we know that C is in units of meters per second, right? So if I indicate that over here, I can be really clear about it. So if C is in meters per second, then we can really see where that per second comes from. I know that lambda is a distance, so if lambda is in units of meters, then I can see that my meters will cancel here in this relationship, and sure enough, hertz is the same as per second, right? And so sometimes when we're not 100% clear on what the equation is that relates some of these things back and forth, even just thinking about the units can give us some important clues about what that relationship is. So nonetheless, the result here is that our frequency and our wavelength are related intimately. When you know one, you know the other. There's no question there whatsoever. So what that allows us to do then is to also relate the energy of a photon to frequency as well. And so we will often talk about the energy of a photon in terms of wavelengths, and we'll often talk about the energy of a photon in terms of the frequency. And realistically, they're interchangeable things. So let's make some adjustments here. There we go. So the energy of a photon can be expressed as Planck's constant times the frequency, which again should make sense because if we're looking at Planck's constant over on the left, we see that it's in units of joules times seconds. So if I take that number and I multiply it by a frequency, which is in units of per second, or 1 over seconds, the seconds will cancel and I'll be left with joules, which is exactly what I would like if I'm talking about the energy of a photon. So putting all that information together, we can now talk about photons, we can talk about their wavelengths, and we can talk about their frequencies in an interchangeable way. And more importantly, we can also relate this to energy, which is a super key thing to be able to do. And that brings us to this diagram. This is a diagram much like the one in your notes, and it's one often used when talking about what's called the electromagnetic spectrum. And the electromagnetic spectrum is really just, all the different types of photons we might expect to see. And so this is just sort of a map of how that works. And you can see up here on the top, what we've got is all different kinds of photons that you've maybe have heard of before. Of course, X-rays, right? So what are X-rays? They are nothing more than light, but X-rays happen to have a wavelength of, somewhere around 1 nanometer. So very, very, very small wavelength. And as we just learned, that means it's a very energetic photon. And they pass right through human tissue, right? So very energetic. And then over here on the other side, we have things like radio waves, that this is, basically what your phone operates on, receiving signals by radio waves. These are on the scale of about 1 meter. So these photons travel a meter, or more before their electromagnetic field, oscillates significantly. So, very different wavelengths, but it is all light. And of course, our eyes aren't sensitive to any of these. We don't see radars, we don't see microwaves, but there is a tiny, narrow little band here that describes photons that our eyes actually are sensitive to. So we've evolved as living beings that has these organs called eyes in our head, and they just happen to be sensitive to a certain range of wavelengths. And so that's usually sort of in the range of about 700 nanometers to 400 nanometers, where the longer wavelength, the 700 nanometers, corresponds to our red colors, and then all the way through the rainbow we get to about 400 nanometers. And this is what our eyes see as the visible spectrum of colors. Okay, so red being the somewhat less energetic light, and purple being the much more energetic light, with, like I said before, a wavelength of around 400 nanometers. So this is really important information if we are going to talk about how light and matter interact. It's important for us to know this information because certain light is going to be able to interact with matter in certain ways, and it would be really important for us to understand what is the energy of that light in terms of interacting with matter, because that's really going to be the key for how we're going to understand where light fits into this whole equation about understanding atoms and molecules. Okay? All right, so now let's talk about light and matter together. One of the earliest, I think, stumbling blocks in the scientific literature in terms of understanding how atoms and more specifically electrons work is a story that involves essentially what's called a discharge tube. And so you're looking at them now. These are called discharge tubes. You interact with these in the lab, or at least virtually this year. And let me just explain quickly what these actually are. So this is a glass tube, evacuated on the inside, except for some small amount of atoms. And so we can control exactly what atoms go inside here. So I've got a series that I'm showing you here. I've got hydrogen, helium, neon, and nitrogen. And so inside each of these tubes is really nothing but atoms of these particular elements. And so when we apply a high amount of voltage to these, in other words, we're going to give a lot of energy to these atoms, what we find is that they glow. Okay, they're like light bulbs. And in fact, this is literally where the term neon lights come from. You pack one of these discharge tubes with neon and put a lot of electrical energy through it, and you'll find that those atoms glow. But what's really interesting about these systems is that it doesn't really matter what the circumstances are. It doesn't matter what the temperature is. It doesn't matter really what the pressure is inside. These atoms will always glow that same characteristic color. So, for example, hydrogen is always this, relatively nice lavender color, sort of a purplish hue to it, whereas helium always looks a little bit different. So helium tends to have, more of a little reddish tone to it. Neon, even more still, almost an orangish type color. And then finally, nitrogen has, again, sort of a more of a purple color. But these colors are very unique and completely consistent, so always the same. And what we can do is, in the lab, what we actually do is we take these discharge tubes and we take the light, the photons that are coming off of these discharge tubes, and we pass it through a prism. So you'll all be familiar with the notion of, some sunlight coming through your window and then creating a bit of a rainbow on the wall somewhere, or maybe you've got some light catchers that are made of glass, and you'll often see the rainbow, spread out because the light is coming through and diffracting through that glass. And so this is an effect that we can harness and make use of. And we do that explicitly in the lab, in particular with experiment number 2. And so what we're doing here is we're taking these photons, we're passing them through a prism, like this image that we're looking at from your notes. And what we're noticing is that, in contrary to white light, where, white light is all the colors of the rainbow together, so all the photons of all the different visible colors flying together, and we pass that through a prism, and the red photons don't change their direction. They don't get diffracted quite as much as the blue ones. And so what happens is all of those different photons of different colors hit, the detector, for lack of a better phrase, at a different place, and it spreads them all out, and we see the rainbow. So we can do that same sort of thing with the discharge tube of hydrogen. But what's interesting is that we don't see the rainbow. We only ever see these very specific lines, right? So there's one over here, the red one, there's a green one, and then there's a couple of blue ones. And, what we can do is we can think about photons, and we can say, well, I know what the energy of this photon is because it has a particular color, right? And I can convert that color to an energy. So this discharge tube of hydrogen is emitting specifically this amount of energy, and it emits specifically that amount of energy all the time. Likewise, I can say that same statement for these others as well. So hydrogen is also emitting this amount of energy, this green amount of energy, essentially. And then also the blue and then the purple. And if you add these 4 colors together, which is really what's being emitted from the discharge tube, so if you're looking at it with your naked eye, you would see sort of a lavender color. And really that's just the mix of all these 4 specific photons that are coming off. So the interesting thing, though, is that the hydrogen atom is always emitting those 4 unique colors. And it was, I suppose, a combination of Rydberg, but also Niels Bohr, who finally proposed what was a pretty convincing explanation for why this is. Both, why does hydrogen only emit these 4 colors? And why does other atoms emit completely different ones, right? So the effect here is that these emissions from atoms tend to be completely characteristic. There is a certain number of lines for every atom, and that can be different. So hydrogen will not have necessarily the same number of lines as other atoms. But if I've got hydrogen, I've always got these 4. And those 4 are always in the same place. So I like to think of these as essentially a barcode for atoms. And it's really interesting because that uniqueness of this barcode is conserved. Whenever you have hydrogen, you see this exact unique barcode. And every other element in the periodic table, if energized in this way, if caused to emit photons, will have a completely characteristic and unique barcode all unto themselves, with not necessarily the same number of lines, but characteristic of that particular atom. So if you know what the barcode is for any particular atom, you can identify it by causing that atom to emit light. Okay, so and the way we cause it to emit light in this particular case is with an electrical charge, but there are different ways to cause elements to emit light. Okay, so we're starting to see the relationship between light and matter. Okay, so there's this interesting relationship. They do seem to be inextricably linked. Matter can emit light. Matter can also absorb light in what would be a very similar mechanism, but first, we need to talk about what that mechanism actually is. Okay, and so it was Niels Bohr who proposed, what is now known as the quantum model of the atom. Okay, so we're going to be talking about quantum mechanics here, which is maybe a sort of a daunting label. We might be, afraid of that sounding like a bit of a daunting subject matter, but realistically, the way we're going to treat it here is quite tractable, I think, for most of you. So the quantum model is really just about changing our ideas about matter from that of a continuous one to something that's a little bit more discrete. So let's dig into that a little.